All right, we'll go from current slide. And we're in Chapter 20, 20.3, Soils. Chapter 20 is Shaping the Earth's Surface. Before we get into this, let's just go over quickly where we left off last time. And then now that I think about it, I wish I'd have done this before I turned on the recorder, because there's going to be a little dead time here. I think at least one of you, or maybe two, were not here last time. Is that right? Were you here? Did you get the take-home test? No. Huh? The what?
Chapter 19.
Yeah, the last time we were here, Tuesday. Were you here Tuesday? Did you get the take-home test? Oh, okay, good. Okay, but you did. Okay. I knew one of you was. I couldn't remember if both of you or not. Okay. And here's Justin. Justin was here last time, so I know he doesn't need it. Another copy anyway. Mark you here. All right. Now, okay. In the last class, on Tuesday when we were here, and here is Christy. You were here last time about the take-home test. Last time we finished chapter 19, but not with enough time to do the lab. So we started on chapter 20, which is where we're going to continue today. Because chapter 19 in the test bank, it was a, thank you, pretty miserable. Ooh, look at this. Hey, research paper in. Yes. Okay. I need to, if I don't do this now, I'll forget to do it later because I'm in such a rush when I finish this class. So hold on with me just a minute. All right. All right, let me pick up again. Since we did finish chapter 19, I gave you, the test bank, the questions in the test bank for this chapter where I felt the worst of any of them that we had done so far. I just I couldn't get approximately 20 questions that I thought were reasonable questions that weren't really obtuse, vague, confusing, whatever terms you did. And finally, I just gave up and made out a test. And because it's fill in the blank, and I didn't want to figure out your spelling, and again, based on some fairly interpretive type situations, I figured I'd go and give it to you as a take-home so you could have your book open. So all of you here got a copy of it now. Okay, so that's where we left off then. So what we're going to do today is start with chapter 20, where we left off 20.3 on page 510 if you're in this current edition. And then at 1:30, we'll stop and have the lab from chapter 19. Now, it's not just chapter 19. All the labs from now on, pretty much, are going to be based on everything we're doing in past chapters and maybe not too much in future. So they won't be tied to one particular chapter. It'll be covering a wide variety. Okay? So, any questions before we get going? So, if I get the running off at the mouth and don't stop by 1:30, stop me, okay? So we can get going on the lab. The lab today is, I don't think it'll take you all that long. It's kind of a fun lab. and you'll be doing a lot of stuff in it and working with each other, that kind of stuff too. And we will go from, I think you'll finish in less than 2 hours, but I want to give you at least 2 hours to work on. Okay? Now, if we finish chapter 20 today, which I'm not sure we will, then if we do, you'll have that lab on Tuesday. And if we don't finish it today, you'll still have that lab on Tuesday, because we'll finish it Tuesday for sure. But if we finish it today, then your test on chapter 20 will be on Tuesday. But if we don't finish it today, it'll just be the lab on Tuesday. So that's what we're going. So what we were talking about so far, this chapter is shaping the Earth's surface, as opposed to chapter 19, which was building the Earth's surface. And part of the shaping part is the wearing away, weathering of the parent material, which is rock. Now, all the rock was at one time igneous rock. That igneous rock was worn away. What 3 types of weathering did we have? 3 types of weathering. First type has actually 2 names. Say again? Okay, not yet. That's what we're going to be doing here. 3 types of weathering. This is what we did last time. A little bit of review. 3 types of weathering. Physical weathering, chemical weathering, and biological weathering. And we talked about some of each of those. Physical weathering has another name. Now I'm going blank on it. Mechanical weathering. Physical and mechanical mean the same thing. Okay, so that igneous rock was worn away. Some of that rock may have been deposited somewhere and then became sedimentary rock. Or some of that igneous rock may have been put under greater pressure and temperatures and actually changed to metamorphic rock. But whatever kind of rock it was or determined, it broke down, okay, and continues to break down. The rock cycle, they're always breaking down. That's the weathering. That type of thing. Part of that broken down rock material forms what we call soils. If we didn't have that, we don't live, okay? Because soils are where we grow our plants and raise our herds or whatever. We've got to have them to live. So what are soils? This is a reasonably good definition. It's a mixture of unconsolidated. Now what does that mean? Things not stuck together. In other words, it's not rock anymore. Unconsolidated, weathered, we talked about the 3 types of weathering, just mentioned them. Earth materials, that means rock that has been worn down, weathered, physically weathered, chemically weathered, biologically weathered, earth materials. And another type of material that is not earth materials is organic material, humus. What humus is altered, somewhat decay resistant, usually plant material. Now, I threw a lot of weasel words in there. I said somewhat decay resistant, okay? Certainly humus disappears, okay? Basically, humus is, I said organic, plant material they say here. That means it has carbon in it. Any compound in it has carbon, okay? And carbon will oxidize away to be carbon dioxide, okay? So it isn't completely resistant, but it is somewhat decay resistant. It says plant material, but it's not always plant. Animal byproduct and stuff can be humus as well. In fact, I read or heard recently, like in the last few months, someone postulating that they thought, okay, let me back up. If I say the soil has a lot of humus in it, do any of you have a clue what that means? What would you picture if I said the soil has a fair amount of humus in it? That's altered, decay-resistant plant material. Say again? Okay, you're absolutely right. Dead plant material. You're absolutely right. Altered in that you don't see it as plant material anymore. I mean, you don't see the little leaves or that kind of stuff anymore. It's actually been broken down until you don't recognize it's plant material, but you know that it one time was. What does that do to the soil? Any idea? Second. Okay, now that's one thing that it's really well known for and given a lot of credit to do is put some nutrition back into the soil, and you're absolutely right, it does. In fact, now my wife felt like I was getting too old and slow to mow the yard anymore, so she now hires somebody to do it. But when I mow the yard, those grass clippings go right back on. I do not pick them up and bag them up and put them on the curb for them to haul off, because I figure lots of chlorophyll is leaving, magnesium, other things that are good for the soil, I want them going back into the soil. Okay? Same thing with leaves. I don't. Yeah. And with leaves, I don't bag up leaves and put on the curb. Of course, she doesn't let me do this either. But when I was doing it, I ground them up either with the lawnmower or with a mulcher machine and spread them in my flower beds. Okay? I did not believe in fertilizing the grass and then sending the fertilizer on the curb. Yeah, so I like to recycle everything I can. So ultimately what happens, and this is sort of what I was fishing for, but you're talking all around it, how you tell if a soil has lots of humus in it, it's usually dark. It's that dark, rich-looking soil, and you say, oh, that probably has lots of nutrients and good kind of stuff. That's what humus is. It's that dark color, because the soils aren't naturally dark. They're usually reddish colored or grayish colored or whitish colored. But with the humus, they get dark and they look rich and fertile. Okay? And they tend to be a little bit better anyway. Now, here's what I heard just a few months ago, it seems like. I don't remember exactly when it was. That all this dark material that they see on the soil particles that they thought were parts of altered decay-resistant plant material, that a lot of this is either the residue from or the dead bodies of microorganisms. The bacteria that break down that plant material, eat that plant material, and then either secrete the used plant material, or else they die and their bodies decay to do that. So it's not always plant material. It can be microbes, okay? And I think that's probably not a bad representation. Jessica is here. If I can find you. I think I just... What's that? Oh, sorry. I put... I'm so far across the page here, I happen to put Christy present in Chris's place, so sorry about that. I'm going to put a question mark by Chris. I think he may be out today, but if he does show up, I've got to be there also. Okay, so that's what soils are. Now, we're going to talk about humus again, but while we're here, let's go on and add to that. A couple things that Christy said. You think of it as adding nutrients, and it does, okay? For instance, the grass clippings, because they had chlorophyll in them, they have to have magnesium in them. So I don't like to give that away, so I don't want to put it on the curb, okay? Now, the leaves in the fall, you know, the plant is taking most of the nutrient out of those leaves that it can. It only leaves the skeleton it can't. So mostly it's carbon and calcium, which calcium is a good nutrient too. So there's not a lot of fertility left in those, okay? But it's still good. Here is the main thing that humus does for you. Admittedly, it adds a little bit of nutrient. But the best thing it does for it, it helps the soil retain water, but give water to the roots, okay? Now that sounds like that's contradictory a little bit. Here's what I mean by that. And we'll talk about later, we'll talk about the different, in fact, the next bullet point here. In fact, let's go and hit the next bullet point, we'll come back to humus, okay? Weathered materials, not the humus, the weathered materials include quartz sand, though it may have other kinds of sand in it too. It doesn't have to be quartz, but quartz is the most common. Clay minerals, metal oxides, salts, and they left out one thing, but it's not a huge major thing here, silts. S-I-L-T-S, silts. Now let's go to those three. They really don't do a great job on this in the book. They mention it, but they don't do a great job. If I were to ask you what's the difference in sand, silts, and clays, would you have a clue? Okay. Anybody? It's not what makes them up. That's not it at all. What's the difference in a sand, a silt, and a clay is how big the particle is. Okay? Now let me start with a dime. Okay, that is a dime. You see how thick a dime is? Pretty thin. That's approximately 1 millimeter thick. Pretty thin. Okay? Any particle that you find in the soil that's at least 2 dimes thick, okay, it's not very big, that's what a sand particle is. That's why I said it doesn't have to be made out of quartz. Most of the time it is. That's the most common sand we have. But it's a fairly small. Anything bigger than 2 dimes put together, thickness-wise, it's going to be not considered, it's going to be considered gravel, basically. And Lauren is here. Okay. Now, for people who just came in, you did get the take-home test last time, right? Okay. Jessica, you got it last time, so you did. Okay, yes. Good. All right. So anything larger than 2 times thick, or 2 millimeters, is going to be considered gravel. Anything 2 milliliters on down to, and basically, let me say this, anything that when you rub between your fingers feels a little gritty, that's sand. Okay? Now, the next one down is silt. Silt could be quartzy material, or it could be other kinds of material. What silt is anything that when you rub it between its, well, not anything, but it's particle size smaller than sand, but when you rub them between your fingers, it feels like flour, right? Hardly any grittiness at all. In fact, a flour or dust kind of texture to it. Now, the clay minerals. If you thought silt was fine, and it is, clay is just submicroscopic. So here's what I want you to do. Picture this dime, and that you had a device that you could split that dime. You could shave off that dime into 1,000 equal slivers, thicknesses. That little bit thin dime, slice it into 1,000 equal slices. That stuff you could almost see through. I mean, it would be so incredibly thin. That's called 1 micron. Okay? 1,000th of a millimeter is a micrometer. Anything 2 microns and below, that's clay size. The particles have to be that small. And guess what? You'll never see a single clay particle. You'll see clay, but that's made up of particles so incredibly tiny, you can't see them except through an electron microscope. The most powerful optical microscope, you'll still never see a clay particle. They are that tiny. Okay? So your clay minerals are incredibly tiny, your quartz sands are gritty, and the silts are in between. Now, the metal oxides. If I ask you what color is clay, what would you say? What color is clay? Say again? Okay, tan or yellow, some people call it red, okay? Always seem to have a color to it, okay? That's not the clay color. The clay itself is a dull whitish kind of color, okay? But these metal oxides, if it's red, it's iron oxide. If it's tannish, it's probably got some other oxides on it. If it's yellowish, it's begun, some of the red clays are beginning to reduce and become a different kind of, but those are all metal oxides. I mean, remember the clays are 1,000th of a dime, is the biggest diameter, and yet all those are coated with these metal oxides. Just every now and then you'll have a metal oxide stuck on the clay. And here's why. Anytime you get anything that small, 1,000th of a dime, you've got charge. Absolutely going to have exposed charge somewhere, positive or negative, and that's going to attract these metal oxides. And they stick to the edges and the plates of the clays like crazy. The salts are things that are usually dissolved in the soil, so these are all the weathered materials. Quartz sand, silts, clay minerals, metal oxides which stick on the edges of the clay or the sides of the clay, and salts which are usually dissolved and hanging around the other materials. Okay. Now, let's back up to the humus again. Do any of you do any gardening, either flowering plants or vegetable plants or any kind of plants whatsoever? Any of you? Not a big thing, huh? Bet your mom or grandma did, didn't it? Okay. If you've ever tried to grow anything in sand, you'll find a really big problem with it. There's actually two problems, but they build on each other. Any idea? Okay, what makes a sand is this fairly large particle size, which means they're fairly large pore sizes in between the particles. Does that sort of make sense? Because particles aren't evenly shaped, so they have big spaces in between. And when you have big spaces in between, big particles, then water flows through it really easily. Kind of like a sieve, right? You do cooking, anybody? Okay, your colanders, your sieves, your water just goes right through. Okay. Well, that's sort of what sand does. So it's really hard to grow things in sand because the water just washes right through. Okay, when it rains frequently, they'll keep growing, doing okay. But when it gets dry, the roots die because they don't have enough moisture to hang on to. Well, what humus does is fill the gaps between the soil particles, the pores, and with this decay-resistant plant material, and that stuff holds on to moisture really well, but it gives it up to plant roots nicely, very nicely, okay? So if you add organic matter, mulch, soil conditioner, anything like that to a sandy soil, you'll probably be able to grow plants a lot better because this humus helps the plant, it helps the soil hang on to the water a little bit better and then freely gives it to the plant roots when they come tunneling in. Let's go to the clay minerals. Anyone ever try to grow much on clay? I guess not, since nobody grows anything. What clays do really badly, they pack down into almost bricks, okay? And that's bad because plant roots trying to get into that, the pore sizes, and by the way, remember the particle sizes are microscopically small, so the pore sizes are microscopically small, okay? Even when it's not been packed tightly, it's still very, 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 very small pore sizes, and since you have small pore sizes, it's hard for the plant roots to get in there and get the water out. Clays tend to hold water really, really well. The bad news is they hold it so well, plant roots can't get it out, okay? If you add humus to clay soils, mix it in, then the humus gets in between the clay particles and it holds the moisture well like the clay does, but it lets the plants, again, have access to the water. Whereas the clays themselves, they're going to stick together so tightly, they don't want the plant roots in there, okay? So the humus, the main thing it does for you is improve water delivery. Okay? It helps hold water in a sandy soil. It helps release water in a clay soil. It's great stuff all the way around. And on the same side, it holds a little bit of nutrient. Clays hold nutrients really well too, but they don't give them up easily. Humus does. Sands don't hold nutrients worth it too. That's the second bad thing about sands. There's just no surface for the minerals to stay on, so they get washed right out of the clay, out of the sand, just like the water gets washed right out. The humus gives the nutrients a place to hang on, so now the plants can get not only water but nutrients as well. All right, that's probably way more than you wanted to know about soils. Now, very seldom will you have a soil that is pure sand. The closest we come to the beach, right? And if you've ever noticed, not much grows on the beach, does it? Okay? It's just white sand. That's because, for several reasons. Number one, it doesn't hold moisture. Okay? And then two, the beach is usually salty too. Okay, so that, very seldom will your soil be pure sand. And if they are, it's going to be hard to grow anything. There's a place when I'm driving home to Georgia, on Farmers Bridge Road, which is getting pretty close to the farm in Georgia. There's a place that just in old, well, actually at one time, let me get the road to point this out to you. There was a time, it may have been back around the dinosaurs and those kind of times, when there were hardly any glaciers at all. The whole earth was very warm, so there was hardly any ice left, so the oceans were quite high. And you see, here is Georgia, okay? And I'm just going to make an estimate about 90 miles up the coast of what is currently Georgia from the Atlantic Ocean. That's where the beach used to be, okay? Because the water was so high, and the other things were happening too, that the beach, because there's a place in my county where I grew up called Shell Bluff. I call it Shell Bluff because you can find shells there in the residue. And this is about 100 miles up the Savannah River, okay? And yet shells were there. That used to be the beach, okay? Now, further from the river, if you go sort of due east or so, maybe a little bit south of there, is where this Farmers Bridge Road crosses, and you can see this great big fields of sand. Well, you don't see the fields of sand. What you see is scrubby little trees that looks like someone clear-cut about 5 years ago and the trees are just growing back. Not the case. These trees could be decades old, but the thing is, they're just there in sand. There's nothing to support it. Finally, one guy came in, bought that real cheap because nothing would grow there, and started selling sand. He started bagging it up and selling it as sand, play sand, sand for people to use for making concrete and stuff, and made a lot of money, I think, selling the sand because it just wasn't any good. It didn't grow anything. And you see everybody's driveway is white, they don't have any yards to mow because nothing will grow there. Well, that's what happens with quartz sand, okay? And similarly, clays, you very seldom find pure clay soils. If you did, you call that a brick factory because, nothing, it's going to be really hard for those soils to produce much. Most of the time, the soils are mixtures of these things. Some sand, some silt, some clay, and then the other stuff, humus mixed in with it, okay? The optimal kind of soil is then not a sand, not a clay, but some mixture of these, and what we call that is a loam. It's a soil containing varying amounts of sands, silts, and clay mixed with an abundance, plenty of humus, which makes the water retaining capacity of that soil quite nice. Now they say it's also known as topsoil. That's not quite fair. You can have topsoil that is not loam, and you can have loam that's not topsoil. So I don't like that definition, also known as topsoil. This is the definition of loam. Soil containing varying amounts of sand, silt, and clay mixed with an abundance of humus. That says it the best. Now, when you have loam as your topsoil, you have a very good, usually a very well, high-producing soil as far as doing crops. See, I'd say the optimum type of soil to have for raising crops. Most of the time we don't have that, especially here in the southeast. We don't have that many loam soils. We have soils that are too high in clays or too high in sands. Okay. Now, the topsoil is exactly what it says. It's usually the top layer of soil. Okay. Now here in the southeast, sometimes you measure that in inches. Maybe an inch or two of topsoil and then nothing. That's why a lot of the fields here don't grow things well, because we've eroded away most of our topsoil and don't have much left. Out in the Midwest, oh my goodness, they measure the topsoil sometimes in feet, because it's really deep, rich, wonderful soil. And a lot of times their topsoil will be loams. Not all the time, but a lot of times they will be. Okay? So that's why the slide says it's also known as topsoil. In certain parts of the country it may be, but not here in the southeast. Okay, so the topsoil is the uppermost layer of soil that's usually the best for growing plants. And sometimes that's just a couple of inches, if that much. Sometimes it's feet, if you're lucky. Okay? Not here in the southeast. You won't find it as feet very much. Okay? Now, below the topsoil is what they call the subsoil. And they say several things about it here, but some of the more important things they've kind of left off. Number one, they say it's less fertile. Okay? And here's why it's less fertile. It contains less humus. Okay? Now, humus contains some fertility, like we said, but what it has is the capacity to hold and release water for plants. The subsoil doesn't have that. It has less humus. Okay? So typically it's less fertile because the nutrients either don't get down there or they wash through it, one or the other. Okay? That's what the less fertile, because the humus controls and holds nutrients as well. Typically the subsoil contains more rock and mineral accumulations. Well, guess what? The mineral accumulations would be positive. They'd be good, because that's where you get your minerals. But if they're tied up in rocks, then the plants can't get to them. Okay? So that's not good. Now, the main thing about the subsoil, the topsoil is usually more porous. Remember, we talked about that before. It has greater porosity, but the subsoil are usually packed together, so it has less porosity. Or if it does have close to the same porosity, the pore sizes are usually very small. Maybe more of them, but very small. So it's hard for water to get into them. It's hard for the nutrients to get into them. It's hard for the roots to get into them. So that's why the subsoil is not ideal for growing. If you have a good mixture of sand, silt, clay, and lots of humus, then the roots, water will get in there and stay there. Roots will be able to extract water, and roots will be able to extract nutrients. Because your humus and your clays are going to hold the nutrient. The humus releases them better, same with water, but the clays will hold the nutrients a little bit better, way better than sand will. Okay? And that, I think, is all they have on soils. Okay? Any questions? Can I move on from here? Okay. Section 20.4 is a good thing to follow the soils with, because this is the problem we have. I've already mentioned it, especially here in the southeast. We lose a lot of soil because of erosion. Okay? Now, other things erode too, not just soil, but that's usually where we talk about erosion. Now, what is erosion? It's the mass movement of soil. It's not like it just loses a little bit here and there. It's usually losing it big time. Now, this is an interesting statement, and I guess I had never thought of it in these terms, but most erosion, I say most, not all, most erosion is caused directly by gravity. Well, everybody has gravity, so it's hard to avoid erosion. Because guess what? Gravity pulls things downhill. That's where we lose our soil. It starts up here on the hillside, on the fields, and runs down. Okay? Two types of erosion based on speed. The first of these is called soil creep. Okay? That's not a creepy soil, but soil creep. It's the slow movement of soil down a steep slope, or any slope. Okay? The slow movement of soil down a steep slope. Now, I can remember when I was in some sort of elementary grade, I don't remember which one it was, reading in, I think it was a social studies book. I don't know if this is all that accurate, but evidently it happened enough that they said it, that it was somewhere in Europe. I'm thinking France or maybe Italy or Germany or somewhere like that, that the farmers would actually go in when they were preparing the fields for the new crop and haul soil from the downhill side and take it back uphill again. Because very slowly the soil is going to creep down the hillside. It just is. Gravity pulls it down. Okay? Now, it has help from other materials, but that's the slow movement of soil down a steep slope. Okay? Now, if it's moving more rapidly, that's called a landslide. Okay? Any slow to rapid downhill movement of materials. Now, when do landslides occur? Any clues, ideas, theories? When do landslides occur? When what?
When waves take place.
Okay.
It moves,
Okay, you're talking about seismic waves? Yeah, it certainly could do it. Now, we just don't have seismic waves that frequently, but we do have landslides probably more frequently than we have seismic waves. So when would that be? When the top level, yeah, just starts falling downhill. There are a couple of things that promote that. One is not around here, okay, too frequently that I know of, but up in the mountains, especially in the wintertime, when snow builds up on the mountains, and then in the spring it starts thawing, and then not just water comes running down, which will cause some problems, but when the snow starts sliding down. We call that an avalanche. Now, avalanche can be either only snow, but most of the time it's not just snow. It can be rocks or other things as well. So let's say we had a mountainside and it was fairly steep, and something up there on top of the mountain loosened a rock or a boulder or something, and it starts coming downhill. Guess what? It's going to start bumping into other things, picking up other things, and that's what creates the avalanche or the landslide. All right. Now, about this time of year, in fact, exactly this time of year, out in California, Colorado, New Mexico, Arizona, a lot of these places, right now, there's two huge ones of these happening. One's in California, I think, and one is in Colorado. Anyone read in the news, heard in the news, some pretty major natural disasters that are happening. One in California, one in Colorado. What time of year is this? Summer, which usually means heat. which quite often, now not for us this year, thank goodness, sometimes drought. And in California, Colorado, they've had basically several years of drought. And therefore, the soil is very dry, the plants are very dry, many of them dying from not having enough moisture. So you have a lot of dead plant material. I'm talking about grasses as well as trees. Dead, dry plant material. And the summer is also a time for thunderstorms. Sometimes thunderstorms come with not much rain. These happen out west a lot. They're just lightning hitting the ground, sparking some of that dry plant material, and starting what? Forest fires. And they have, I was hearing on the way in today, I think they said in California, one that was now 138 square miles has been burned. And I pictured that in my mind. 10 miles one way, about 13 miles the other way. That's a big area that's been burned. Hot burn, too. Colorado, it seemed like theirs was about 100 square miles. 10 miles by 10 miles. Huge areas, okay? Burned. Burned hot. Burned almost completely, okay? Now, next spring, those areas are probably going to receive, and the people hope they receive, fairly large spring storms. And what's going to happen then? That area that the plant material was on, basically protecting the soil, has been burned off, and now you just have soil there, and when it gets hit by a lot of rainfall, mudslides and landslides. So landslides are caused either by rocks falling down a hill, snow going down a hill, sometimes water going down a hill, just something that creates an issue, so the slow to rapid movement, downhill movement of materials, mostly of your soil, even though it could have rocks and logs and other things in it. We've been on a couple of trips out west to the mountainous areas out there, and you'll see you'll be in forest for a while, and then all of a sudden you're not in any trees at all. You look uphill and you can just see where the avalanche has just wiped out everything. You see logs at the bottom and stuff like this. Any slow to rapid movement, that's landslides. Slow movement, soil creep. You don't actually see it, but you see that it has happened. This is, to me, a gross exaggeration, but you can see this on some hillsides. And the trees tell you the soil is creeping downhill. Because up here on top, that tree is pretty straight. Further down the slope, you can see it's got a bend. Because you see, the canopy's always going to try to reach up to the sun. But the base is being washed out from under it, so it bends to try to keep reaching toward the sun. And more you go downhill, you see more and more bending of the trunks. Now, I've never seen this in huge degrees, but obviously it does happen. What happens is soil, see, the rock underneath here has been worn away to produce the soil, and the steeper part, most of the soil is eroded away, and the sort of shallower part is still going downhill. It's very thin at the top and thickens at the bottom, but it's creeping down the hill. And you can tell that by the vegetation. That's soil creep. If it happened rapidly, even the trees have gone down the hill. They're no longer in the soil. Okay. Now, two types of erosion. The mass movement, soil creep, that's just the soil moves downhill due to gravity. Another is running water. Okay? Now, before we do this, there are some examples in the book. 20.1 is what is the slope and percentage grade for a mountain road that drops from 2 kilometers elevation to 1.2 kilometers over a distance of 3 kilometers. Well, that's just measuring a slope. Change of rise over change of run, rise over run. So you can do that. They just made up a problem to try to fit it in here. Example 20.2, what is the gradient of a stream in meters per kilometer that drops 8 meters over a distance of 2.4 kilometers? Again, it's just a division problem. Okay? 20.3, in 2010, a class examined a graveyard to measure the displacement of tombstones by the process of soil creep. By measuring the tilt angle on the various tombstones, they determined the displacement to be shown as on this table, and they show you the farther back in time, the more the displacement. The nearer in time, less displacement. So it then asks for about how much do you expect that soil to be moving per year. An example 20.4 on the next page, 512, very similar measurements of tree trunk angle and displacement. They go through the same type stuff. And then the concepts applied are creeping trees. And frankly, I've never seen enough of this to know for sure. But if you do see some, you can try this on it. We have a big old pine tree in our yard. We have 2 big old pine trees in our yard. One stands perfectly straight, the other is tilted. And I have no clue why. They're both on level ground. There's no soil creep involved that I can tell. So you could be measuring angles that have nothing to do with soil creep. But obviously in some mountainous area, you can measure this a lot better. So under erosion, first is mass movement by gravity alone, pulling the soil downhill. Soil creep or landslide. The second way that soil gets eroded is by running water. And again, this is a gravitational process. And this is the most important of all the gravitational erosion processes. Running water moves more soil than landslides. More soil than soil creep. This moves the most of it. The most important of the gravitational erosion things. They say 3 stream transport mechanisms happen. Okay? Now I want you to flash back to a few chapters ago, when chapter 17, I believe it was, where we talked about the lithification process of sedimentary rocks. You remember what 2 features you had in the lithification process of sedimentary rocks? Okay. The first was compaction, and the second was cementation. Compaction pressed out the soil pores and also squeezed out some water perhaps and made the things closer together. And then cementation was the dissolved minerals and stuff in the soil now was gluing basically the soil particles together. So you had soil compaction and soil cementation. Okay. Now with running water, or any water standing on, water is a great dissolver. It's one of our best solvents we have out there. And this water running through a soil material is going to dissolve some of the materials that help hold the soil together. We're not talking about rock anymore, we're talking about soil. It also has materials that sort of hold it together. We call that characteristic soil structure, how it clods together, and that helps in the plant roots, you know. If the dissolved materials that sort of hold it together are washed away, then the materials are loosened and they're more easily carried away. Secondly, suspended materials, okay? And I think you've seen this probably. After a very heavy rainstorm, what do most of your creeks and streams look like? Second? Okay, they're flooding, and is there any difference in how they look, the actual water in the flood? Yes, brown, red, you can't see through them. Whereas that normal stream, you can look down and almost see the bottom, can't you? But when it's a rush, now it's carrying, those are suspended materials. Now the dissolved materials don't change the color of water any, suspended do. And when it looks murky, muddy, that type of thing, you have lots of suspended materials in it. Especially after a heavy rain, you get a lot of it. And then the third, if this is really rapidly moving water, you have rolling, bouncing, and sliding materials along the stream bed, which are doubly bad. Number one, they're moving downstream, but they're also, when they're rolling, bouncing, and sliding, they're picking up other things off the stream bed and carrying them downstream too. That's especially bad. Now, I want to go back, and I wish they had said this earlier. They may actually mention it in the book, but they don't on the slide set. There are two, I think I've mentioned these before, two major components to this transport. In fact, transport is the second one. The first is detachment, and then transport. This is the transport side, but the detachment process is also inferred here. And here's what I mean. The other day, was it yesterday or over the weekend? Sometime or another, my wife and I were out in the yard working, doing some stuff, and it just began raining. And when it started raining, they were these great, big old, heavy drops that started. It wasn't like this fine mist that then developed into rain. I mean, these came just a few big old drops, and when they landed, they made a splat. You've seen that? I can remember one time when I was a very young boy, my father, sometime during the summer when the crops were kind of taking care of themselves and stuff, we'd take the week off. He was a farmer, and we'd go up to North Carolina. We were from Georgia. Drive up to North Carolina to see the grandparents, that type of thing. His brothers and sisters too, my aunts and uncles, and cousins, play with the cousins. And I can remember riding down the road in the summer sometime, and all of a sudden these great big old drops would hit the windshield, and almost scary. They just splatted on that windshield. Now that's coming from, and here's Caitlin. Okay, couldn't quite get your name out. Okay. This happens a lot in the summertime. And they said there was a chance of rain today, and when I got out of my vehicle in the parking lot this morning, I looked at the sky. There was not a cloud in the sky. I said, where is the chance of rain coming from? But because they said that, I kept my windows up. Normally I would have lowered the windows to get that clear. But I look out there now, and I see quite a few clouds. Now, if I saw among those clouds, I can't see them well enough because there's too many tree limbs and leaves there. But if you see these clouds, those ones that look like a big anvil top and go way up into the sky, that's called a cumulus cloud. We're going to talk about that in the next chapter when we do weather and climate. Okay? The cumulus clouds. Those are ones that sometimes reach way, way, way up into the sky. And those are the rainmakers. And quite often, and we'll talk about this next time, those raindrops are falling from way, way high up there. In fact, those big old drops of rain that fall like I was describing, most of them were at one time hail. Heavy, heavy chunks of ice. Okay, we'll talk about this in the next time we do, when we talk about weather and climate. But they fall from a great distance, and the farther they fall, the more speed they pick up, and if they're picking up mass, they have mass. Well, guess what happens when you have both a lot of mass and a lot of energy? I'm just getting away. A lot of speed. you have what we call kinetic energy. Kinetic energy is 1/2 the mass times the velocity squared. So the faster it's falling, the more energy it has. When those things hit the surface of the soil, they detach the soil particles from where they were sitting. And then, because the rain's coming, they transport them away. They dissolve materials, they suspend materials, and they haul stuff off. So that's the two parts. First the detachment, then transport. Now, how do you correct for that? How do you minimize that? So if you've got your flower beds, or your vegetable beds, or whatever your crop you're trying to grow, or things you're trying to grow, if you can keep a layer of mulch on that, that can absorb that energy and not detach the soil particles. And then that hits the mulch and it sort of dissipates the energy, the rain falls through, and it seeps into the soil really slowly without detaching it. And then what's more, that layer of mulch is going to keep the moisture there. If you had exposed soil, when that sun comes out, which usually happens in the summertime, you can get a shower, heavy rain, we did yesterday, and about 15 minutes later, here's the sun out again. And it's so steamy and hot and sticky outside because that's evaporating every bit of that water up that it can. Well, if you're doing that off of raw soil, then you're losing the moisture. So the mulch is really going to help. Okay? And that's why I don't like taking up the grass clippings or taking up the leaf mulch. I want it staying on the ground. It's going to help them move a long time. Okay. So let's get back to running water. Things like mulching and other things like that will help slow down the erosion due to running water. Now, they are now getting into another area. This is leading into the next slide. Stream bed evolves over time. But I think we're going to have a slide here first, so let's see what happens here. Ha! There's a heavy spring rain. I almost guarantee the grass looks like it's fairly new and growing. And this is coming down the side of a hill. This is coming down. What you notice about this water? Brown. I wouldn't want to drink this water. Why? It has suspended materials all over in it. That's soil that came from up the hill there, up the hill there. Soil that was on the ground is now being hauled off by the water at pretty rapid rates of speed. Okay? The suspended materials are being hauled downstream pretty significantly. Okay? Now, like I said before, the last slide was leading into the next slide. Stream bed evolves over time. And here's what they're talking about. Let me go on and get the first picture up here. Okay? When a stream is developing, early in the time, that water is running down usually pretty steep slopes. The landmass has been recently uplifted. Now, we're talking geologically recently, like in the last few thousand years or so. It doesn't seem recent to me, but to the soil, it's pretty recent. The landmass recently uplifted, you have a steep gradient, meaning the water is going downhill really fast. Because the steeper the thing, the faster it flows. And the faster it flows, the more it carries. Kinetic energy, remember? You have a steep gradient, and that makes these steep V-shaped valleys with hardly any floodplain at all. Do you remember the picture right at the beginning of the chapter of Yellowstone? The Yellowstone River, that pretty waterfall, I think it was the upper Yellowstone Falls, falling down, and then that stream bed rushing down below. Remember those valleys? They were V-shaped. There was no roundedness to it. They were V-shaped valleys early in the formation. Now, they think that Yellowstone was developed by a fairly recent volcanic explosion. Thousands of years ago, but still fairly recent. And that's why the landmass there is very young, very new. Hardly any floodplain where the water slows down. You have boulders, rapids, and waterfalls all over. Now, these don't show any, but that one in Yellowstone did show. Rapids, these things are just really moving. And waterfalls like we saw in Yellowstone. In a more mature landscape, what has happened, in this case, tens of thousands of years to have happened, the erosion has occurred and the sharp peaked mountains have sort of rounded out, deposited soil materials into the valleys. So now these aren't as steep, these are filled in, so now the streams sort of go more slowly. Okay? The stream gradient is smoothed and lowered, reduced. Now it meanders and you have floodplains. If you have a heavy rainfall, probably all this green area here is probably going to flood. Probably not a lot of flooding up there, maybe along the sides and the banks. Here, it just runs downhill until it finds a floodplain. Okay? But here, these areas that are sort of not got a lot of rise or run out of them, they're going to flood more. Okay? Meanders, the streams sort of wander around. Now, in a very old age landscape, you have very low gradients. There's not much difference in elevation here to here. So the water moves really slowly. Broad, gently sloping valleys and sluggish flow. And if you have heavy rainfalls, huge amounts of flooding. Okay? Now I want to point something else out to you that you see in these older landforms. I have a picture here they don't mention. Okay? What in the world is this right here? It has a name, they call it a bow lake. Okay? Now, how did that bow lake develop there? Well, here's my guess. I think this is pretty true. This river or stream happened to once probably flow over here. Notice there's not much difference in elevation. It flowed over here and had a bend here and then wandered around like this. And over time, I don't know what caused it, it eroded more back here, and now the stream changed direction and left this lake over here detached from the rest of it. Okay? If you can find a map of Louisiana, Mississippi, any of the states along the Mississippi, and I don't know if you've ever paid a lot of attention to the grand old lady, the Mississippi River. I don't know if this will show it, but it really doesn't well enough. But the Mississippi River is anything but straight. Mississippi River does this kind of stuff all over the place. And if you look at the states on either side, you'll see these low lakes that are just out there. And you think, why is this lake here? Because the Mississippi changed its course. It dug out a deeper place somewhere else and left some water way over there. So those are characteristics of these old age landscapes. Okay. Ha! Here it is again. What should this be? Youth, maturity, or old age? This is youthful. Look at these valleys. Shoot, straight down. That is a V-shaped valley. That's the youthful landscape. Waterfalls. You don't find waterfalls in these. This is, see how jagged and cut this is. This is very young. Only a few thousand years old, probably. Huh? That's Yellowstone, exactly. This is, I think, the upper Yellowstone Falls, and the rock over here, yellow color. That's where it got its name, Yellowstone National Park. Okay? Right near the entrance to the park from the Wyoming side. Beautiful place. If you please, sometime during your lifetime, try to get to Yellowstone. I mean, it's a bucket list type thing to do. It's a huge park, so give yourself a few days at least. A week would be better, but not many of us can afford a week. But when you first go into the park, there's all these pull-offs you can look at and go over and take a look. You see one waterfall up here and another one downstream there. You can hear it better. You can walk on down and get a view of that one as well. Just incredible. The Yellowstone Lake, when you first are coming in, huge lake. It's inside part of a crater of an extinct volcano. You think, oh my, that was one massive volcano. And then later you get on further in the park, you'll see the geysers, you'll see the mud pots, you'll see the cauldrons, you'll see just more geological features than you will in that size area anywhere else on the globe. It's just a phenomenal, phenomenal place. Okay, and before I turn the page, in your book, and maybe some of these are going to show up later, but I kind of doubt it. Here's a picture of a river running through some really well covered soil, because you've got lots of trees and you figure other things, but evidently it's been a rainy season because look how murky the water is. So even though you have a lot of soil cover, it still creates a lot of loss. Now this landscape, what would you say about this one? Look at the bow here and the river. I mean, it's just, that river is meandering like crazy. Very low. This is a old age landscape. And guess what? A lot of rain happened upstream. Lots of these fields will be flooded. Okay? Great soil because it's been deposited there over years and years and years, but highly prone to flood. Now, example 20.5 and 6 here. Each year a major river in the humid region transports, and it tells how much sediment eroded from the drainage area. And you think, oh my goodness, that's tons and tons and tons are being eroded in a given year. It's just incredible. So just reading through the numbers, even if you don't do the math, it's really amazing. Okay? The next page is, I can't tell if that's the upper falls or the lower falls. This looks like the upper falls, which makes me think that may be the lower falls, because they sure don't look that similar unless you just got a different angle. Maybe that's it. They look pretty similar, but not exactly. That's the Yellowstone River in Wyoming. Indicate that the river is actually down-cutting the V-shaped cross profile, lack of a floodplain characteristic of the young stream. Okay. Example 20.7 talks about how fast water must be running, blah, blah, blah. Average depth of the. Okay. So there's stream development. All right. If you go on downstream to those old age, very low gradient, broad, gently sloping valleys, what you run into there is called the deltas. These are deposits. Now, this book really doesn't do as much of a job as the previous book did on your yeah, it's here too. Okay. It's just on the next page. Okay. Deposits of sediment at the mouth of a river or stream. Okay? Now, the biggest river system in North America is they usually call it the Mississippi-Missouri system. Mississippi is a long river, but actually Missouri feeds into it. And Missouri is a longer river, covering a huge amount of area, and it flows into the Mississippi. And when you combine them together, that's an enormous amount of water going downstream. And when there's enormous amounts of water going downstream, you got enormous amounts of soil being carried downstream. And if you look at, and this is not the best to see, but what is it, the mouth of the Mississippi? What state is that? where the Mississippi runs into the Gulf? Second? Okay, Mississippi is over on one side of it, where it actually flows in Louisiana. And if you look at Louisiana, don't you see how it sort of sticks out into the Gulf of Mexico? Okay. Watch it on weather maps and stuff. You can always pick it out because it sort of protrudes in the Gulf of Mexico. You know why? Because soil has run downstream all from the Midwest, the far west, from all over the place. And as it's come down, it carries sediment and carries sediment and carries sediment. And that sediment is dropped off at the mouth. And actually, most of Louisiana, or at least a big portion of it, is sediment that's washed from way upstream. Some as far as Canada, okay, and being carried down. The stream flow dissipates into the ocean or lake, and when it dissipates, it slows down. When it slows down, it drops stuff that's been carrying along for a while. The erosive and sediment carrying abilities are lost, and they drop the materials at the base. And these are called the deltas. And this is the figure you have in your book. Here's a picture of it. Now, I don't know, do they say where this is? They make it seem like there that this is from somewhere up in, and it could be from up into, say, the Great Lake or something like that, because they mention Wisconsin, and that would be unusual. But it's there. If this is Lake Superior here, yeah, all this stuff is happening there too. Okay. Notice flat. Okay, with streams cutting through it like crazy, like you see here. All this land. This is I guess what they're suggesting is the native bedrock here, okay? And then the river has come down, deposited material, and stuff. And once the beach was up here, now it's out here somewhere, because you have all this soil, not just what you see up here, but everything underneath it has been deposited there over centuries, millennia. Lots of time as more and more stuff has been dropped off there. So these deltas grow. Okay? They name several features of it here. You don't need to know this, but I can't read all of them. Let me see if I can read them in the book more. The bottom set beds, those are deposits that probably come out of the water itself. The foreset beds are the ones that are sloping like that. They came from upstream. The top set beds, those are the most recently deposited. Those are more horizontally layered. And then the marshy delta surface is that one there, and the distributaries, which is one way to phrase it. Your land is back here, and who knows, that land may have one time been marshy land, but it's just built up enough we think it's the native land. And maybe it is. The way they show it, that probably is. But all this has been deposited over time. So frankly, in my mind, the state of Louisiana is probably 10 to 20% bigger than it probably was a couple thousand years ago, because all this deposits have come down, forming these deltas. And they don't just happen where it runs into a big body of water like the Gulf of Mexico. A river running into a big lake will still have these characteristics happen. And you can't see all of this, but you sort of see a hint of it. This is what you see on the surface, but what's underneath there goes way out into the water. So these are gradual, shallow areas here. Man, if you get a major rainfall upstream, then lots of this could be flooded. Now, is that bad, wasted stuff that we should be able to do something to control that? let's not try, okay? Because these marshy, wetland areas like this, they do a lot of filtering of stuff. Some good stuff, some bad stuff, but they keep it from flowing into the, say, Gulf of Mexico or into the river itself, lake itself. If you tried to improve this situation the way we think of improving, you might get too great of river run going through here, and all of a sudden you've eroded things away. I mentioned how the Mississippi winds like crazy. The Nile River did the same thing, and someone got an idea, hey, we could control the flooding downstream if we had the currents moving more rapidly upstream. Maybe. What they wound up with is eroding away lots of good topsoil, and it went all the way to the Mediterranean Sea rather than deposited. So now the farmland that kept getting flooded, bringing good, fresh, new soil in, it wiped out the crop one year, but then the next 3 years you have fantastic crops, and then maybe another flood, and then 5 years you had great crops and stuff. When they fixed it so it didn't flood as much, suddenly those farmers downstream, the land wore out really quickly because they didn't get the recharge. So a lot of things we think are really good ideas turn out not being such good ideas. Okay. That's a little advertisement for how stupid people can be sometimes. Never mind, I didn't say that. Okay. How are we doing? Thought y'all were going to keep up with for me. Isn't it right at 1:30? 1:29. So I think we probably need to stop at Glaciers. Okay? Pretty cold place to stop, isn't it? What's that? All right. So we'll stop at Glaciers, and that's, by the way, after Glaciers we'll talk about wind, and then we'll go back and develop some landscapes again. So we'll finish this chapter, I think, in the first 15 to 30 minutes probably next time. So let's look ahead. What we're going to do now is the lab that would have been for chapter 19. And then on Tuesday of next week, we'll probably finish this chapter pretty quickly and have the lab for this chapter. And then we'll have the test. No, I'm sorry. Well, chapter 19, I've already given you the take-home test for. Yeah. So we don't have a test coming until Thursday, probably, on chapter 20. Okay, so today we'll stop and have the lab for the last 2 hours. Tuesday we'll have an hour and a half of class approximately, and then 2 hours for lab. So Tuesday will be a lot like today, only we'll be finishing chapter 20 and probably starting chapter 23. And then Thursday we'll just see how it goes, but definitely we'll have the test on chapter 20, the last 30 minutes on Thursday. Okay? Everybody got it? All right. I'm going to pause. All right. We don't need the glacier thing here anymore, so I'll get out of that. The lab today, I don't know where the rest of them are, is on latitude and longitude. Now, they talk about this on the first page, page 339, and they define these various terms here. I'm focusing on the ones that are bold-faced. Okay? Let me get my board back out. I put it up because I thought it'd be in the way, but let me get it back out. Okay. We talked about this before. The equator is a parallel, okay? It's the main one. The only great circle parallel we've got. 0 degrees north, 0 degrees south. It's right smack in the middle. Then you go up these parallels, and you see there's slices that get smaller as you get toward the top. But these on this one are at, pretty sure 15 degrees, but I got to find one that's listed. There we go. Okay. 15 degrees north, 30, 45, 60, 75, and 90. Same thing going down. If I can find it. Where was it? There it is. Oh, there we go. 15 degrees south, 30 degrees south, 45 south, 50, 60 south, 75 south, and then 90 south. Those are your parallels. They run east to west with a measured angle north or south of the equator. That measures your latitude, how far north or south you are above or below the equator. So when you're giving a latitude, it's going to be so many degrees, may have a few minutes, and on very precise maps, you may have a few seconds, okay, listed on there, okay? Now, you have these other lines on your globe that are all great circles, and they all go through both the North Pole and the South Pole, and they cut through the latitude lines at 90-degree angles. These are your meridians. They're all great circles, and you're so many degrees east or west of the prime meridian, which of course is through London, Greenwich, England. Okay, the prime meridian. That's 0 degrees. And so you go, and again, they usually measure these on this one on 15 degrees, 30, 45, 60, 75, 90, 105, all the way around to 180 degrees east, and the same 180 degrees west. How far east or west you are. The lines run north or south, but they're measured east or west from the prime meridian. Okay, those are your longitude lines. Okay, those are the longitude lines. This is all on the first page here. Now, we don't have under the materials any soft clays. We're not going to do that. Okay, but it's good to think of this. The picture here, if you cut that globe exactly along the equator, only halfway though, and then slice down, say, right here through London, England, and over here to the prime meridian and international dateline, slice through there, this is what you would see. And you see you have 0 to 90 degrees north here. If you cut the lower half, you'd have 0 to 90 south. But here on east-west, you have 180. Okay? Now, we don't have a clay ball, but you can visualize this. You can visualize putting a protractor there on this surface, and it goes 0 to 90 north for either direction there, or flip it over 0 to 90 south in that direction. Okay? Also, you have, if you place it on the flat part, the horizontal part, 0 to 180 degrees east from the prime meridian, or if you flipped it over backwards, kind of, you could do 0 to 180 west if you measure the prime meridian close. Okay, so read the stuff. Okay, it's several pages, 339, 340, and 341, and then see if you can answer the questions under the results on page 342. Okay, 5 questions there. I would hold off the 5th question for just a little bit. Okay, now that's only 5 points worth. You got 20 points worth yet to go, and here's where you get those 20 points. Okay. We've got 8 cups up here. One of these is Africa. One is Alabama. One is Asia. One is Australia. One is Canada. One is Europe. One is South America. And one is the U.S. Okay. Now, in each of these cups, you'll find on little strips of paper the name of a city. Okay? It's my writing, and so it's sometimes hard to read, so if you can't make it out, ask me. What you're to do is to draw from this cup, and you can either use other paper if you want to, or the back of the sheet. Don't your papers have a blank flat page? Yeah. So let me hold that through. Okay, so on the back of the piece of paper, and by the way, let me point out to you, question number 3 on page 342. According to a map or a globe, what is the approximate latitude and longitude of the place where you live? Here's the Alabama Atlas, and this is where you'll find the place where you live. If you open it just about to where it falls open in the middle, this is on pages 30 to 31, I bet you the vast majority of you live somewhere on this page. Okay? Living on this page, then find the latitude that you'll find right this way, and you'll be all north of the equator, and then the longitude you read this way, you can either read on the top or the bottom, and that's how far east or west you are from the prime meridian. So find your location and then estimate, and these will be to minutes, degrees, minutes, and seconds. Okay? So that's your answer to number, I'll give you that. Okay, number 3. And while you're at it, doing that, go on and draw from the Alabama cup the name of one additional city. Write that city on the back. Blah, blah, Alabama. You'll have to go to some other page in this one and give the latitude and longitude of that city. Okay? Now, draw, and I wouldn't draw them all at once. I would draw one at a time and write it down. Draw 1 or 2 from Africa. Of course, I already said 1 from Alabama. 1 or 2 from Asia. 1 from Australia. 1 from Canada. 1 or 2 from Europe. 1 from South America. And 1 from the U.S. Okay? Now, there's 8 cups. So I already mentioned 1 from Australia. From Alabama. 1 from Australia. 1 from Canada. And 1 from South America. And 1 from the U.S. That's 5. Okay, 3 more cups. Draw 1 from each of those cups. And then from 2 of those 3 cups, that's Africa, Asia, or Europe, draw a second count of the 4 cities listed in there. So, draw a piece of paper, write it down. 1 from Alabama, 1 from U.S., 1 from Canada, 1 from South America, in any order you want to. 2 of these cups, either Asia, Africa, or Europe, 2 of those cups draw a second. So you have a total of 10 cities listed on the back. 2 out of either Africa, Asia, or Europe. 2 cities out of 2 of those cups. Not all 3 of them. You just pick which continent you want to draw 2 from.
What do you say, draw? What do you mean by draw? Oh, okay.
Yeah. I see that. Now, if you think that it's wrong, and I think that was wrong, I just drew out of Africa, Jerusalem, Israel. That belongs in Asia. Okay, so if you think it's wrong, ask me, I'll get it. Because see, I've had students do this for years, and they'll put them back in the wrong cup. That's why I say, draw out one, write it down, put it back in the correct cup. Okay, that's why I said do it in that order. Don't draw them all out and then try to remember which cup it went to. Draw one at a time. And if you think it's wrong, ask me and I'll let you know. Okay, so the one from Alabama, number 3, and the one from Alabama, you'll use this Gazette. Okay? The one from U.S., you'll use this one. All the rest of them, you'll use one of these 3 atlases. Okay? We'll move a little out of the way again. Okay? Now, this is a lab. You can work together. You can work individually. You can work however you want. You've got to answer the 5 questions. One of those is a latitude, longitude question. And then draw 10 cities out of the 8 cups that I described, writing them down, putting them back, write them down, put it back. Okay? And then for the Alabama, use this one. For the U.S., use this one. And for the other parts of the world, Canada, Europe, and everywhere else, use one of those 3. If you have trouble finding, ask me, and I'll help. Okay? Any questions? You write down latitude and longitude. And by the way, when you're writing down latitude, you need to put so many degrees. If you're using Alabama, you can probably put so many minutes and so many seconds. Okay? If you're using the US, it's probably just degrees and maybe minutes. If you're using the others, probably just degrees. You put down the number of degrees, but you also have to put a direction. What two directions can you choose from for latitude? North or south. Put N or S. If you leave that off, you don't get it full credit. Okay? And longitude, again, you can give me degrees, minutes, and seconds from here, probably degrees and minutes from there, probably only degrees from those three. And guess what? After you give me that, you have to give me one or two letters. No. East or west? E or W? East of the prime meridian or west of the prime meridian? What's that? Okay. Okay. Make up. Well, let me turn on the projector. Okay. Okay, I'm going to make up a city that I do not believe is on that, is in there. Okay? I just happen to be looking at China, so I'm going to pick, okay, here we go. Can you read that yet? All right. Now let's just say it won't be in one of those cups. Here's Wuhan. Let me get my pen set up. Okay, the city. Okay. Wuhan, China. W-U-H-A-N. I'm sure this isn't in the cup. Wait, in China. Okay. Latitude. Longitude. Now this is not very precise because I'm using the globe here. The latitude for Wuhan, China is, I'm going to say 31 degrees north. Okay, if this was in Alabama, you need to give me minutes and seconds. US, I think you can do minutes, and most of the other globes, atlases, probably only degrees. Since this is China, that's only degrees. Wuhan, China, that many degrees north. Notice I put the N there. And then Wuhan was 25. I'm going to estimate 110. 110 degrees east of the prime meridian. That's it. Okay? And again, if you were doing out in Alabama, you're going to give me minutes, seconds, degrees, minutes, and seconds. Probably out of the U.S., degrees and minutes. And out of the others, you might be able to get minutes every now and then. Mostly it's just going to be degrees, just like I did there. Okay. And first, draw it out, write it down, put it back. Draw it out, write it down, put it back. Okay? You want me to leave that up a little bit? Okay, just tell me something. I just did that, and I don't think I turned on the... Yes, I did. Okay. I did start the recording again. So I'm going to pause the recording until and unless there's other questions. But I'll leave this up. Some of you came in after I received it, but I finally got my first paper for this class. That was fantastic. So keep them coming, folks. That opened the floodgates to start them flowing. And get them here as soon as you can. Don't forget to do your paper. All right. That was the advertisement.